Could you start recording? Oh, okay. So today we're going to read this paper, and I would like to talk a little bit about some of the authors, although our guys are going to talk a little more detail. So Ingrid Blanchard was working as a postdoctoral researcher with Dave Ruby, and they have been, and the second author, Dave Ruby, he worked on quite a lot in the recent, I would say, recent 2 decades at least. Earth's core metal differentiation process, including the Earth different accretion process. And the last author, Morbidelli, who is Italian and worked at Nice University, France, and he developed a model called Nice model. So basically, they were the first group of people who used one-body simulations to show the formation of different planets, in particular for the Earth. So this work also partly used some of the Nice model. Is a Grand Tech simulation as they have been showing there. So the author Blanchard continues with different parts of the components that Dave Ruby has been added in for decades, from the highly sensitive elements to other type of volatile elements. So in this work, they pay attention to carbon and Wences-Tag and Blanchard are also going to talk about sulfur. But in general, it is within the same topic of the core metal differentiation process. So with that, Arka will leave the task for you to let everyone to going through this paper. Go ahead, Arka.
So good evening, everyone. So today we will read this paper by Ingrid Blanchard, as Professor Zhang said. So this paper mostly deals with the partitioning of carbon during Earth's accretion. So here's an outline of today's presentation. So we will get to know about the author, the speaker who is coming on this Wednesday a bit. We will see about the problem statement, and we will go for the results. And then on the later part, we will see about the behavior of carbon in Earth's accretion, during Earth's accretion, and the conclusions from this paper. So Ingrid Blanchard did a PhD from IPG, and presently she is a postdoctoral researcher at Potsdam University. Her interests mostly lie in the early differentiation of Earth into the two reservoirs, that is the silicate Earth and the mantle and the core. She does perform various HPD experiments and laser heated diamond anvil experiments, which is which was used in this particular study as also. So here are some of her recent publications. So if we see that carbon is a siderophile element at low pressure temperature, carbon behaves as a siderophile element, and ideally, so it should be very much enriched in the core, and the mantle should be depleted of carbon. However, we see at the bulk silicate earth enrichment, or the concentration of carbon at bulk silicate earth, it's almost around 100 to 260 ppm. So the question that, or the objective of this work was to explain that what leads to such enrichment of carbon in the bulk silicate earth. So as pointed out by the authors of this work, the previous experimental studies were carried out at low pressure temperatures, but at more putative conditions, that is the formational conditions of the core, that around 49 to 71 gigapascals and of a temperature of 3600 to 4000 Kelvin, the siderophile behavior of carbon decreased. So they also added a few parameters, like they took into consideration the core mantle differentiation based on the accretion simulations, and they were able to explain the present concentration of carbon in the bulk silicate earth. So if we see that carbon is both a volatile and a siderophile element, so the metal silicate partitioning does not only depend on the core mantle differentiation process, but it also depends on the volatilization that happens during the core mantle differentiation and the accretion processes. So the few models that were proposed previously were the imperfect metal silicate equilibrium, and the core outgassing from the core once the differentiation process was over. As the pressure temperature increased in the core, carbon became less siderophile and it outgassed into the mantle. However, recent experimental studies at the core, which are conducted at uh, at a higher temperature pressure near to the core formational pressure, core formational conditions, showed that the siderophile behavior actually decreased prior to the differentiation. So Fisher, there was a work by Fisher prior to this work where they did the similar experiments. However, due to or they couldn't come to a conclusion as their experiments from they did two kinds of analysis from nanosims and from EPMA, and there was an uncertainty in order of magnitudes. So the authors in this paper prepared the sample in a very similar way. However, with some further constraints and better TEM analysis, they were able to show the and combining the parameters of this core accretion, they were able to show the present bulk silicate at core carbon enrichment. So if we look, so on the figure that shows on figure A, that is basically the sample that they had prepared. Figure C and figure D are of interest. In figure C, the gray blebs that we see, they are basically the metallic exsolution phases. When scanning transmitting electron micro STEM or EDS analysis was done of the same area, we could see the enrichment. So if we look at the green blebs on figure D, they are the oxygen rich phases. The blue are the silicate rich phases, and C and the red ones, they are the carbon rich phases, which are believed to be exsolved diamonds. So why is this texture of why the textural study is of importance? Because this is from ACM. Because previously from ACM analysis, these blebs were not visible. So the chemical analysis that was done, they didn't consider the difference between these blebs. So if we see at the STEM images of the crystalline area, we see that there are two kinds of metallic blebs. One, you can see that the big distinct blebs, blue ones, you can see, and there are minute, smaller metallic blebs. So the idea was that, or the conclusion from while they did the analysis, they took into consideration that this they could avoid the big metallic blebs, and they didn't take their data. And it was that in high temperature pressure silicate melts, it is obvious to have such metal concentrations. So that was pretty much with the previous works. But the smaller blebs, they weren't, due to the spot size of nanosims, they were not able to exclude them. However, uh, their conclusion of this small metallic blebs was that uh, during the quenching process, the silicate phases, they didn't turn into glass as predicted, but there was an intermediate crystalline phase. Now, this when crystalline phase was passed on to further quenching, they formed the glass. They formed the glass. The brickmanite that was initially formed further dissolved, and this exsolved metallic blebs are from that. So after when they did the analysis based on the textural studies, they excluded the bigger metallic blebs and they further constrained the studies. This was the difference in their data, the red triangles that represent their data that they observed with respect to the partition coefficient, distribution coefficient, and that of temperature. And on the right hand side is that of distribution coefficient and that of pressure. So these differences were observed. So further, when they did the the results were divided into two kinds of studies. One was textural studies, and based on which they did the chemical analysis, and then they did the thermodynamics. So to so what they took is they calculated the oxygen fugacity based on the iron oosterite buffer, because at high pressure temperature, iron oxide and iron partitioning is obvious. So they took the iron oosterite buffer, and what they observed was that the partitioning coefficient, which was previously stated that it was above 100, uh, was found to be a few magnitudes lesser, around 23 to 157. And in order to uh, negate the effect of this oxygen fugacity, they took the distribution coefficient, that is the KD, and they did the experiments with two valencies, one with at carbon plus 2 and carbon plus 4, because usually methane is present in the fluids, and over there carbon occurs as plus 4. So during this experiment, they did the major constraints. So one was that their initial sample was that of the mid-oceanic ridge basalt composition. So they took samples, the previous literatures from where they have taken the data. They took the data which fell into this category. They also avoided samples that were calculated at buffer of iron oxide buffer of less than -3, and they avoided taking samples that were calculated at very high pressure temperature. So following that, they were able to show the partitioning coefficient that actually explains today's carbon enrichment in BSE. So if I look at the summary of this result was of the results from this paper were one based on textural studies and one based on thermodynamics. So they used the textural studies from TEM to actually exclude the large metallic inclusions. They were able to say that the inclusions in silicate, the smaller inclusions, were due to Brigmanite exsolution. And from thermodynamics, they were able to. So the previous studies, they only considered the silicate melt composition, the carbon metal interaction, and the oxygen fugacity. Is someone saying something?
No, it's just my voice has to be on. Go on.
Okay. So, however, in the present study, so NBO by T constraint is basically non-bridging oxygen per tetrahedra. So it is one of the constraints that the researchers usually put in order to see the differentiation of carbon at different pressure temperature. So this constraint was added. They avoided low concentration of light elements. They took samples that had the concentration of light elements were less, because their interaction with carbon is not significant, but on a larger scale, the values tend to skew the data. And the rest 2 points I have already said. So these were the constraints, and by that, what happened was that they were able to say that not only the carbon that we find in the bulk silicate earth as of today is not something that has been entirely produced during the differentiation process, but they show that the chondrites that hit the earth during the accretion process. So if we take the chondrites beyond 4.5 astronomical units, these chondrites were highly oxidized, and they led to the enrichment of carbon in bulk silicate earth, whereas whereas carbon that was present in the metallic meteorites or metal enriched meteorites, they went directly into the core. So one of the explanations they give is that if we take a continuous accretion core mantle differentiation model that continuously the carbon was partitioned, they were able to show that at the formational temperature of the core mantle differentiation, carbon cannot be the efficiency of carbon getting into the core was very less. So the continuous process was not what was happening, but it happened through years, through series of impacts. And as they show in the next figure, So they used an accretion model that I don't have a very good idea of planetary sciences. So I really don't know how the model works, but it's something called the Jantax model. So over there, they can estimate the number of accretion and they can find out the total carbon enrichment that happens due to N accretions. And from there, they were able to get these values. So over here, what we see is the carbon enrichment during Earth's accretion. So over there is the ball cut, and we can see the mantle accretion. And on the right hand side, so these are both with, so on the right hand side, we can see with time, they have shown that how the carbon enrichment actually changed in the mantle. And that was the major work of this publication. So the key take home points of this publication is that at high PEP, carbon becomes significantly less acidified. And one more thing is that the value they suggested for the BAC was 140 with an error of plus minus 40 ppm carbon concentration in the borosilicate earth. And I think I just discussed the rest of the points in the presentation. So that would be all.
Okay, thank you, Arka, for the presentation. Any questions for our participants? Okay, I read this paper a little bit before, but not for today. Because I would like to say something that's a little bit relevant. So when I think there was Rebecca Fisher. Sorry. So it was Rebecca Fisher about 3 years ago in the published paper in PNAS, and mentioned about the carbon partitioning between the metal and the core is have a partition coefficient very, very low. That is, the carbon is not a siderophile. And I forgot the exact number, maybe 1 to 1, 1 to 3, is that the core could contain a lot of carbon, which is big, put a lot of controversy in the community, because people used to think that carbon extremely siderophile, like approaching the end member of like platinum, for example. And Rebecca's work trying to say, no, it's the other way around, that the carbon is not a siderophile at all. But that is one of the controversy about is that in Rebecca Fisher's work, when they analyze the carbon contents in the silicates, they analyze. I think there were two controversies about it, as far as I could recall. So one controversy is that they analyzed, for Rebecca Fisher's work back then, they analyzed the standards using nanoseams that has a relatively low carbon concentration. And then in their results, the carbon concentration is a little bit high, much higher. Then they extrapolate for their calibration curve to something really high. I think maybe 1 order of magnitude higher in the silicate metals. I forgot the exact number, but you could tell me that, prove me I'm wrong. Maybe the carbon content is up to 1 weight percent with 0.1 weight percent. It's very high in silicate melt. That's what the Smithsonian group reported. And this is one controversy about it. I think the other controversy that Rebecca Fisher was pointing out is that when they analyze it, it's very hard to avoid the metals quenched within the silicates. So those metals might be the core metal, but happen to mix with the silicates. So you analyze the silicates, mix with some metal, and then you get a very high carbon concentration. Maybe most of the contribution is coming from metal, which is not the silicates. So basically, if you talk about silicate and metal partition coefficients, then you significantly overestimate, right? Because the silicate content, carbon contents in the silicates are not true. So I think this work is partially motivated by that work to a certain extent, because a lot of people in the community disagree about that. But I think as a science, we always have some disagreement and people do more work to verify or disagree. So Arka, according to what you introduced earlier, it looks like what Rebecca Fisher said was not fundamentally wrong. Maybe their numbers, the partition coefficients are not exactly the same, but it looks to me that what they represent, that carbon is not cellulophile, too cellulophile, or much less cellulophile with increasing temperature and pressure. And therefore, we won't expect the core mantle differentiation to very efficiently strip carbon from the mantle to the core.
Yeah, so this paper actually brings up the points that you just said. They do oppose Fisher's work in two cases. One is that they say that it was taken in the experiments were performed, the samples were prepared at extremely high pressure temperature. So the siderophile behavior was already decreased. So that is one thing. And second, what you said that, yeah, while Fisher's work, I think it was in 2020, it was published. So over there, they didn't do the TEM analysis. So what they got is just the quenching product as the glass. So they were not able to differentiate between the metallic blebs, the metallic inclusions in the silicate melts. So their carbon concentration was already very high because they took the metals which carbon was present in the silicate, and that was the product. And after that, they extrapolated. So they do say that carbon behaves less siderophilic, like during the core mantle differentiation process. But I think that what this paper tries to tell is that the core mantle difference, even more than the core mantle differentiation process, it's about how the metals got enriched in the DSC. So they take into point the accretion parameters. So that is what I think this paper is all about, if my guess is right.
Okay. Okay, that's good. Okay. I have another question. So for the size of what they did in this work, including Rebecca Fisher's work, is that their entire sample size is about 100 to 200 microns, right?
I do need to cross-reference that.
Yeah, you will go back to their showing their samples. Could you go in there? Could you moving back to the slides?
Yeah, sure.
Yeah, I think it was maybe third slide at the beginning when you showed. Okay.
No, I'll just go to the paper. Yes.
It's just very small. It is very small. Actually, it's less than 100 microns. It's fine. It's fine. I think, yeah, you could go to the paper. So because my question here is that even in their work, that the sum are still quite small. I mean, it's great that they analyze that, but the analytical challenge is still there. To solve the quenching problem is not easy, and get large samples better. So Lei, I have a question for Lei. So Lei, did you remember that? What's the size of the 19 GPa experiments that you have in your samples?
So I think what Ben is asking something.
Okay.
So Ben is asking that.
Okay. I just quickly read Lei's results. So it's about 500 microns. So because Lei used some multi-angle experiments to study also carbon under the deep upper mantle transition zone pressure all the way up to 19 GPa. And there's a paper that was just accepted by ECA recently. So in that work, so for Lei's case, the sample set, but do you mean 4-hole or 1-hole experiment? That's 0.5 millimeter. like this 1 hole or 4 hole, 4 hole. I think you do have some 1 hole experiment, right? So is that size for 1 hole? So for 4 holes, so that's in total. So could you say it is 4 hole? No. So could you type if you do a 1 hole experiment by 19 GPa, what is the size of the sample? Okay, so 2 millimeter, that's extremely large. So if you look at what they show here, maybe 50 microns, 100 microns. So what they could reach for 19 GPa is 2000 microns. So that's many times larger than what they have shown here. Okay, so Arka, please read Ben's question and then address from your side.
Yeah. So Ben asks this question that how were they able to calculate the bulk carbon composition in different phases of the sample after the experiment? So the thing is that they didn't calculate for different phases. They only calculated for the silicate phase. So if I look at this picture, let me go down in the paper once. So if I look at this picture, so see the green part, which is over here, this is the silicate major part, and this blue parts are the blue and red, they're the metallic. So, but they were able to exclude these parts. So this blue, is my pointer visible? If it's so over there are two blue blebs. So they were able to exclude. They were able to exclude these parts, but they do say that they weren't able to exclude the finer metallic inclusions in the silicate melt phase or the silicate phase. But for that, they have an explanation that during partitioning, so in the mantle also, when Brigmanite will break down, it will give out the metal phases. So it is so the greener part in which there are other metallic inclusions that can be considered as a silicate phase of the bulk silicate art. So they did the analysis only for one phase. They didn't go for the other phases and computed the bulk carbon composition. So I hope that clears Ben's answer. Okay.
Actually, that brings me with an interesting comment that in my mind is that, okay, since the sample is super small, I think they have another disadvantage compared with what Lei has been doing, is that once the samples are too small, then you cannot just weigh them and say, okay, what's the bulk carbon that you put in? Because all your bulk composition just weighed several micrograms or even lower than that, then you just have too large uncertainty. And for Lei's case, she could get to several, I think, micrograms, I think, so that she could measure it more accurately. So I think for this large volume apparatus, we know that bulk composition much better than this demo animal cell experiments. So that's another thing that made me think good about it, is that the multi-animal large apparatus, multi-animal experiments could push something to this high pressure, but with significantly larger volume, which has another advantage, not only for analysis of large samples, but also has this advantage of knowing the bulk composition, I think. So Arca, may I ask that how did they explain with the MB over T? Maybe you went it through fast. I didn't follow so well.
What did they explain? Can I get a question once more?
The MB over T, the non-bridging oxygen per texture.
Okay, so I'll just come to this part. So then somewhere over here.
Okay, Arca, you can look a little bit. I could read and answer Umi's question. So is there an earlier model or experiment that consists of peridotite melt composition instead of the basaltic melt composition? The answer is people all wanted to do peridotite melt because that's what the composition where a mantle should be in the magma ocean or in a core mantle differentiation. But the technical part, experimental challenge for it is that the quenching rate of the experiment matters. That is, once you start with the peridotite melt, you need to go to very high temperature first. Second, you have to drop the temperature, bring the temperature down fast enough. And so far, I don't think people are very successful in doing that. And therefore, you put the peridotite melt and then you don't quench fast enough. Basically, you are going to crystallize a lot of silicate minerals. So, it's very hard for you to keep a peridotite melt. And therefore, people tried and we didn't work so successfully. And actually, there are a lot of dirty secrets behind it that people even, like I say, during the quenching, people produce metals, even though people don't study metal silicate differentiation, only study the peridotite melt. You only put the peridotite melt, quench it, you might produce metals. That all are due to the quenching effect. So basically, the cooling rate of the experiments are not fast enough to quench the peridotite melt into peridotite glass. So that's the challenging part. So that prevents people from doing so. So to make things easier, people do basaltic melt. Actually, that's only in more recent years. And before, people mainly use andesite melt. That's more felsic, and it's easier to quench, and it melts at lower temperature, and easier to control. And then people try to manipulate it by using the MB over T. So because from mafic to felsic, we have different numbers of non-bridging oxygen per tetrahedral. So that's how the business is working on now. I think that there's still a lot of work that could be done to push the technical challenging part to get the real peridotite melt and knowing all kinds of the properties it has. I think another approach is that what you know, Umi, is that people will do this in molecular dynamics simulations. So that's, I think, in the very near future, that's a more feasible way of approaching this problem than relying on the progress in the experimental progress, which I think it is possible. You won't be so fast. And the molecular dynamics probably, from my perspective, will be an approach that is feasible in the next 5 to 10 years. Not the quenching peridotite melt though. Okay, Arca, please go ahead.
Yeah. So as we know that the non-bridging oxygen per tetrahedral, that's a low pressure parameter, and it affects the distribution coefficient of the partitioning coefficient of carbon. So since their samples were taken, so what they did was they could constrain the study. So over here it's written, if you see the highlighted part. So since their samples were of MORB basis, so the composition of that was of mid-oceanic ridge basalt silicate, the silicate composition. So they could constrain this. So that is the only thing that they could do. So they included in the partitioning data. So they took this range. So while collecting the sample space, while comparing with other studies, they took this range that what would be with that of the MORB basalts and the silicates from the MORB basalts, and they did it. So of the many constraints that applied, this is one of the other constraints while performing the calculations.
Okay. Actually, I forgot the range of the MB over T range.
Okay,
For
they're given
from,
that 0.56 to 1.34.
no, not theirs. I mean,
Okay.
for the rhyolite. So do you know the range for rhyolite? I mean, for rhyolite, andesite, basalt, as well as pyrrhotite melt. Of course, four of them will have different MB over T values. Yeah, I would like to see some numbers by that so that we can relook at this. But anyway, this is something that we could look for. I will look for it later on by myself. Okay. So how did they add iron in the experiment? Like, ask a question.
So that, yeah. So they had like the part that I am sharing over the starting materials, the highlighted part. So if you see that they had taken a mixture of oxide and carbonate compounds, and they did add iron oxide to it. So that is what they did. But since I have no idea about, I have very less idea about how experimental petrology samples are made. So I have no idea about how iron was added to it. Like they don't explicitly say anything else.
Okay.
Over here, they do mention something about iron.
Yeah. I think they just add this metal with the silicates. So for silicates, they propelled it with levitation. So basically, you have a how to say, you have a part that is blowing the gas. So which here they call it, I think it's argon. So this argon is the argon flux. So they put the argon flux that flowing up so that you have some metals to stay in there. So argon flux going up so that you could conquer the gravity of the silicate pellet. So, and it's still heated up, so at a very high temperature. So basically your silicates starting material going to melt into droplets like pellet, and it didn't fall. So that you keep this. And the reason they use the argon flux is that they try to prevent this silicate melts to react, because you put it like a carbon dioxide or some other gases that is going to react with the gas. So that's how people do it to form a silicate glass. And then people use that glass to mix silicate glass to mix with some metals. And then that's how they start with their starting composition. So it's a little bit different preparation technique than what Lei you have been working on in large volume apparatus, because this sample is too small. You cannot just depend on your mechanical mixing to make everything homogeneous, because these things are 100 microns. You have several couple grains, and then basically mess things up in your starting composition. So by this, using this levitation, argon gas flux, basically you can make sure that you have a homogeneous silicate glass to begin with. Well, in your case, you have a starting composition of several milligrams. Then you have a lot of grains. Then you don't worry about this small scale heterogeneity, because even though you don't mechanically mix them perfect, but they're close enough in this 2 millimeter by 2 millimeter scale as what you have been working on. So for those bulk compositions you have been working on, you could just say what you mechanically mix should be well mixed. That's more reasonable, but not for their case, for diamond anode cell experiments. Next question, please. Okay, Lei, could you, Arka, could you stop sharing screen? And maybe Lei, you can share your screen so that people see your operators and your samples. Yeah, even not convenient for you to open the mic, I could speak for your behalf. Okay, we could wait for a minute or two. Okay, and for Ingrid Blanchard, this work is quite interesting. I think it's still ongoing debate that the people nowadays pay particular attention to the volatile accretion to the Earth because they're relevant to the habitability of planets, including the Earth itself. And I think it's still a controversial part because this volatiles are not easy to measure and work on. Even for those highly saturated elements, people still have some debates depending on the process that how it has been accreted to the Earth. But to me, that those analytical results for these hydrosulfide elements, as well the isotopes, are more stable, are more reliable. Like osmium isotopes, for example, those communities have been working on for a while, and it's good that those elements they are not volatile. So the process, the fact those cellular hydrophile elements are less, I would say, than what are the possible ways magnetism could affect volatiles. Because, for example, I'll give you one example. So for the magma ocean, for example, very hot magma at the Earth's surface, it could evaporate into the space. But for that process, actually, don't worry too much about this process to deplete the deplete platinum for the Earth's mantle. Okay, it is going to bring a little bit of platinum from the mantle, but it won't just get rid of that. But for volatiles, it might bring a lot of volatiles into space, just lose them to the box silicon mantle. So it's possible. Okay, so Lei is showing this. Since Lei probably is in her office, and I'm going to speak on her behalf. So what you're seeing here, extremely large samples compared with what people reported in this paper for them animal cells. So this is what Lei has been working on for some multi-animal experiments. So Lei, could you share people how big is your operators? Maybe it's not in this, and in your PPT or somewhere. You have the size of your samples, I think. Oh, not samples, but operators. 2,500 tons. 2,500 ton. That cherry one that produce your samples. I think you do have a picture in your poster. Right? Could you share with us that part? Because people could see that your sample is just several millimeters, but people didn't see the operators. You have the operators. Could you go to your Goldschmidt poster? Yeah, everyone, you can see that 10 GPa, 1450 degrees C, 19 GPa, 1450 degrees C, 1600 degrees C. So for that apparatus is pretty large, and that's a 2,500 ton multi-ample operators. Originally from the magma factory in Japan, but later reinstalled in Guangzhou Institute of Geochemistry in China. So Lei has been using that apparatus for 2 times, each time for half a year, has been working on that. So this is some of the work that Lei has been putting on. But in this part, Lei didn't add too many silicate, didn't react the silicate with metals, but it's more about the metallic system to see what are the stable phases for the carbon. Lei is going to represent that as a poster at the Goldschmidt meeting, and but there is a paper that accepted, so we should be able to see the paper in press soon, in a couple months from now. Okay, thank you, Lei, for sharing this part with everyone. So, any more questions or comments, or share with us some of the interesting things? Okay, Wumi, could you share with us about your defense? Yeah, if you have some pictures, do you mind to share your screen and show some pictures? Maybe if you have got them. I bet somebody must have taken some pictures of your PhD defense at IIT India, right?
It was actually online, so somebody like this. It was in Google Meet. So there are some of the images that people had clicked, but mostly they had made memes out of it. So yeah,
okay. But
I don't have them in my laptop.
Yeah, I think how about after party? Because people, you gather with other people for party, right?
Yeah, we went, but I don't think I have them in my laptop. I have it in my mobile.
Okay. Okay. Could you log in your mobile by Zoom?
Yeah. Just I can like I can take some like 2-3 minutes and then I can share this.
Okay. Sure. Great. Okay, Natasha, do we have your defense picture? I mean, that was a year and a half ago. 1 year ago, right? You defended it 1 year ago.
Yeah, about 1 year ago. But I don't have pictures. I don't have pictures, but I do have a full video. It was recorded. So yeah, but unfortunately, it's in Russian, so I believe it will be useless.
Yeah, would you mind share the beginning and the end? We can skip the middle.
I don't know, actually. I've logged from my phone. Wait a minute, I will try to search for some of it. Oof, that's a tough question. The tough stuff. Give me a few minutes. I will search for it.
Okay. Okay, I'm going to point the next person. So Trentao, did you have any of your defense picture? If you could share at least one picture of your master's defense last year. Or Aka, or any of you, how do you have your defense? Because all of you must have at least your master's defense. So could any of you share at least one picture? Maybe everyone, if you could, fine.
Yeah, I can show a picture. Here. Just let me open it.
I'm also going to try to find one for my defense picture.
So I just have only one picture. So
that's okay. Everyone could share at least one picture. Yeah, could you share a screen?
is it visible?
Not
is
yet.
it visible?
Yeah, I can see that. Looks good. That's good. Okay, those all are your committee members, right?
Yeah, those. I don't know what's happening with Zoom. It's acting weird. It just got closed. Anyway, yeah. So those were my. We actually have we have to defend it twice. Once in front of the internal committee members, and once an external examiner comes in. So this was in front of the internal committee members, I mean faculties from my department.
Yeah, could anyone else to share your defense picture? At least, I think everybody could share at least one picture of their of your defense time.
Yeah, I found some fragments of the video. Wait a second, I just tried to learn how to share my screen on the telephone. Can you see my screen?
Yeah, not yet, but I think it's going to pop up very soon. Yeah, I can see your screen. Okay, could you go ahead?
Добрый день, меня зовут Студина Наталья, и тема моей работы – это физико-химические условия образования и эволюции физических пород из ксенолитов якутской киндерлитовой провинции. Вопросы формирования и эволюции земной коры Донецкой до сих пор являются дискуссионными.
So,
Okay,
did you see anything?
Yeah, I can see it. You speak much faster than you're speaking English, I think.
Yeah, I was told that one man after my presentation told me like I was speaking with a hammer and tried to scare everyone around me.
That's okay. I think you speak with passion. It's great. So anyone else?
Yes, I can share my screen. Is my screen visible?
Yeah.
So this was actually my because
Yes.
the presentation was online. So this is some of the pictures that my friends had clicked for me. So it was like there is no video, but these are the so these are there was like the cake was cut after that. And this was the after party where we went. These are these are all.
Next one is going to share your defense picture. Okay, that's good. The next one, please. I'm still looking for mine. I find the data around defense. I haven't found my defense yet, but I should be able to locate one. Okay, Lei, could you share yours? Okay, so that was the day, I think probably the second day or third day after my PhD defense. Oh, actually, I was the most senior people in this picture back then because most of them were first or second years. That was with my PhD student, my PhD advisor, my PhD committee chair. Actually, the person on the left is going to give a talk this summer at our webinar. So the sum of that, of me aging with the years, and the sum of the group picture that I used to have when I started my PhD in August 2011, and at 2 months before my defense. Okay, yeah, that's it. And this one was at the beginning of my PhD. That way, people had a field trip, and we have really beautiful deformed rocks, and they is at the in the Craton. So that's a northern Minnesota at Duluth. It's really good. Actually, it's too bad I didn't find it, but I think I addressed this 2019 September. That was the day when I defended my PhD defense. So that was addressed. Okay, that's all. Okay, I think that's so much for today. And thanks everyone for your participation and sharing. Looks like the defense by Zoom has become a trend that is more prevalent. People are going to have some on-site, off-site combination. Okay, with that, have a good day, and let's see the speaker on Wednesday. Have a good day, everyone. Bye-bye.